The objective of this lecture is to provide two examples of kinematics in rotating and translating reference frames. Before getting started with the examples, it is important to understand what is meant by a rotating and translating frame. So suppose I have a frame, and I call this frame A. And I have a point O, and O is fixed in A. And I have another frame. Let's call this frame B. The frame B does not share a point common with frame A. So if I call this frame B, there's a point Q that I'm going to say is fixed in B. So Q is fixed in B. It's not fixed in A. And then I have another point, call it P. It doesn't really matter what it is. It's some arbitrary point P. And I'm interested in the motion of P. So if I'm interested in the motion of P, you can see that if I break the position of P relative to O, I'm interested in the motion of P relative to frame A. So if I say the position of P relative to O is what I've defined there as the vector that I've just drawn, you can see that the position of P relative to O is divided into two parts. It's divided into the position of Q relative to O and the position of P relative to Q. Now, let's look at this for a second. Let's understand what's going on. Q is fixed in frame B. And O, I should put this above, is fixed in frame A. So that means that Q translates relative to reference frame A. Now this is a really important point because confusion always comes in with these kinds of concepts, because it's often the notion that a point rotates, but points don't rotate. So I'm going to write this down. Points do not rotate. The only thing a point can do is translate. Let's write this clearly. The only motion a point can undergo is that of translation. Now that may seem a little strange just because when you think of a point, say, moving in a circle, you say, well, the point is rotating. But the point's not rotating. The point is translating. It happens to be translating in a circle if you say it's translating in a circle relative to another frame. But that is the only thing a point can do, is translate. So in this particular case, Q translates relative to reference frame A because it's not fixed in reference frame A. It's fixed in reference frame B. Now I have a point P. P is an arbitrary point. So the motion of P can be decomposed into two parts. Now it can be decomposed into the motion of Q plus the motion of P relative to Q. So let's write this down. So the position of P relative to O is equal to the position of Q relative to O plus the position of P relative to Q. So now this is where rotating and translating frames become a little bit confusing, because how do you break the motion up into different parts and keep track of everything that's going on? So when we compute the velocity and acceleration of Q and the velocity and acceleration of P relative to Q, these two parts are kept separate. So this is very important, is that the velocity and acceleration of Q as viewed by an observer in reference frame A is computed separately or separate from the velocity and acceleration of p relative to q, again, as viewed by an observer in reference frame A. So all that means is that when we want the velocity of p as viewed by an observer in frame A, that's equal to the rate of change in frame A of the position of p relative to O. But the position of p relative to O has been divided into two parts. It's been divided into the position of q relative to O plus the position of p relative to q. So when we compute the derivative to get the velocity of p in frame A, what we're saying is that the rate of change in frame A of the position of q relative to O is computed separately from the rate of change in A of the position of p relative to q. And it may actually be advantageous, and often is, to do this separately anyway, because it's just going to wind up making things a lot easier, as we'll see when we get to the examples. So what this says is that the velocity of p in A is equal to the velocity of point Q in A plus the velocity of p relative to Q in frame A. And then if we take the derivative again, we get the acceleration of p in A is equal to d dt in A of the velocity of p in A, which is equal to d dt in A of the velocity of q in A plus the velocity of p relative to q in A. And if we just go through the formal process of finishing this, we get the acceleration of point P in A is equal to the acceleration of point Q in A plus the acceleration of P relative to Q in A, where all I've done is, if you go back, d dt in A, if you really want to take one more step, I suppose one more step may be useful here, just to be clear about it. But this becomes d dt in A of the velocity of q in A plus d dt in A of the velocity of p relative to q in A, which then gives that the acceleration of p in A is equal to the acceleration of q in A plus the acceleration of p relative to q in A. Now that may sound a little bit long-winded, but what's really going on here is as follows, is that let's go all the way back to the beginning of this study. We started with two frames. So we started with a frame A. We've got A and B are reference frames. And what's important is that B translates, or I should do it in the same order, rotates and translates relative to A. The point that defines the translation is point Q. The point Q fixed in B defines the translation of frame B relative to reference frame A. Now, it's important to understand that only defines the translation. It doesn't define the rotation. The rotation of reference frame B relative to reference frame A is still defined the way it was defined before, is defined via the angular velocity of frame B in A. The angular velocity of reference frame B as viewed by an observer in reference frame A. So we've got two things. Notice that the translation and then the rotation, right? The translation of frame A is defined through point Q. So if we write that down, since Q, because Q translates, relative to reference frame A, that implies that the velocity of Q in A and the acceleration of Q in A define the motion of Q relative to reference frame A. And that makes some sense because the frame B is translating and rotating, so now we have a way of defining the motion of Q, and Q defines the translation of frame B relative to frame A. So now we know everything about the translation of frame B. So that implies that Q, or I should say the motion of Q, defines the translation of B. Reference frame B relative to reference frame A. And now the angular velocity is the thing that defines the rotation of frame B relative to frame A. So now we have a complete description of how frame B is moving relative to frame A. So now let's get to the examples. Now the examples themselves are designed to be instructive in the sense that we're always going to decompose the motion into two parts. And this is the last point I want to make before we actually get to the examples, which is that the motion of Q and the motion of P relative to Q need not be expressed in the same coordinate system. In fact, in most of these problems, you don't want to express the motion of P relative to Q in the same coordinate system that you describe the motion of point Q. So I'm going to write that down. So in fact, in most problems, it is desirable to use different coordinate systems to describe the motion of Q and the motion of P relative to Q. So let's go through the examples now and let's see what we're doing, how we would do this. So here's the first example. Suppose I have an arm and it's hinged at the ground. And the length of this arm is L. Let's call it L1 actually. So I'm going to have two arms. And this point here, O is fixed in G. So O is fixed in frame G, which is the ground. And at the end of the arm is a point Q. I'm going to use the exact same notation as what I used earlier because I just want to make this simple for people to be able to make a correlation between the theory and the example. Now, Q is itself a point on the end of another arm. That other arm I'm going to denote it here. And on this arm is a collar that slides. And that point is P. Now the distance from Q to P, that distance I'm going to call this R. So what I'm interested in is I'm interested in the motion of point P relative to the ground. Now in order to be able to do this so that it's easier to understand what's going on, I'm going to define two angles. These angles are going to be as follows. The first angle is going to be called theta 1, and it's measured relative to the rightward direction, or whatever, the horizontal direction if you want to call it that. The second one is going to be an angle theta 2. Now theta 2 is going to be measured from the direction of OQ to the direction of QP. So this is theta 2. So let's understand this again. Theta 1 is measured from a direction fixed to the ground. Theta 2 is measured from the direction of the first arm. And in order to be able to parameterize the motion, you can see that there are two rotations. So I need three frames. So these three frames are going to be the ground, and then the two arms. So let's call the second arm, we're going to call it B. So let's give ourselves enough room here to be able to write everything out. And we're going to say G is the ground. That's our base frame. But before we get there, we need two other frames. So I'm going to say B is going to equal, in this case, it's going to equal the QP out of page plane. The origin of this coordinate system is going to be at Q, because Q is fixed in the second arm. The first direction, I'm going to call this direction, I'll call it U1. U1 is going to be along QP. U3 is going to be out of the page. And then U2 is going to be U3 crossed with U1. Now, going back, the first arm is the one that rotates relative to the ground, so the second arm rotates relative to the first arm. So I'm going to call this the OQ out of page plane, and the directions here aren't going to be that hard, but the origin is really important. The origin of this coordinate system is going to be at point O, because I got to tie this back to the ground, and point O is fixed to the ground, but point O is also fixed to the first arm. So I'm going to call E1, E2, E3 equal to U1, U2, U3 when theta 2 equals 0. So make this really clear. This is a theta 2 equals 0. So when I zero out that second rotation, the coordinates that are fixed in the second arm are going to be lined up with the coordinates fixed in the first arm. And then the last frame, it's going to have a coordinate system, or the first frame, it's going to have its coordinates fixed in the ground, and this is going to be E1, E2, E3 is equal to little e1, little e2, little e3 when theta 1 equals 0. So now let's go through and let's write down. Now look, you'll see that the setup here is exactly the same as what I had derived in the abstract when we weren't working with a particular problem. I have a point O fixed in the ground. The ground in this case is my frame A, if you want to call it that. It's what I defined in the theory or in the concept as being frame A. The second arm is my frame B, which I'm calling frame B. But you notice that the way that this is set up, I actually have more than one rotation here. Whereas in the theory I only had 2 frames. Here I have 3 frames. So what's actually happening is I need that intermediate frame because I have a rotation. But in the end, I've got a rotating and a translating frame. I've got actually 2 frames that rotate. Frame A rotates, frame B rotates, but frame B is my rotating and translating frame. But you'll notice that the position of P relative to O, if you write it down, the position of P relative to O is equal to the position of Q relative to O plus the position of P relative to Q, which is exactly what I had done before. Q is fixed in frame B. Q is fixed in the rotating and translating frame. So let's write that down. Q is fixed in the rotating and translating frame, which is exactly what I said earlier when we were doing this in the abstract. It's fixed in the rotating and translating frame, which in this case is frame B. So point O is fixed in the base frame, but I have an intermediate frame because I also have a second rotation. That's okay. There's nothing wrong with that. It's just that I have a rotating and translating frame, and that's the important thing, is I have to take into account that. Now, if you work through this now, you'll see that the position of Q relative to O is equal to L. I called this thing L, so let's put it back. So L is equal to L times E1. The position of P relative to Q is equal to R times U1. Now look at this. You'll see that they are expressed in 2 different coordinate systems, and they should be, because if the second arm weren't there, the only thing that I'd be looking at is the motion of point Q, and the motion of point Q is most easily expressed in the coordinates fixed in frame A, which are given by the basis E1, E2, E3, which is what I would want to do because that would be a standard polar coordinate system. Similarly, let's suppose that I started with the first arm as if that were like my base frame. Then the motion of P relative to Q would be most easily expressed in the coordinates fixed in frame B, which are defined by the basis U1, U2, U3, which form a polar coordinate system relative to the first arm. So that's exactly the way I've got this expressed. The position of Q relative to O is expressed in coordinates fixed in A. So let's just write down. Position of Q relative to O is expressed in the coordinates fixed in the first arm, which makes sense from the perspective of the geometry. The position of P relative to Q is expressed in coordinates fixed in the second arm. So we've broken the problem up into exactly what we need to break it up into. But now, in order to be able to compute velocity and acceleration, I don't put everything into one coordinate system. So let's repeat that. Do not express each part of the position in the same coordinates. Leave them separate. because it was most convenient to be able to express the position of Q in the coordinate system fixed in frame A, and it's most easy to express the position of P relative to Q in coordinates fixed in B, leave it that way. We're just gonna keep it exactly that way, and we're not going to change anything, and we're just going to differentiate each piece separately as if the other piece didn't exist. So now I know that the position of P relative to O is equal to the position of Q relative to O plus the position of P relative to Q. Now, given that, the velocity of point P in frame G is going to equal the velocity of Q in G plus the velocity of P relative to Q in G. But what's the velocity of point Q in frame G? Well, that's equal to the rate of change in frame G of the position of Q relative to O. But now look at just that part of the vector. Look at the position of Q relative to O. The position of Q relative to O, is expressed in coordinates fixed in the first arm. The first arm is defined by the frame A. The second arm is defined by the frame B. So the first arm, given that it's defined by the frame A and the position of Q relative to O is fixed in coordinates fixed in A, this is equal to d dt in A of the position of Q relative to O plus the angular velocity of A in G crossed with the position of Q relative to O. This is the straightforward application of the transport theorem now, because we already have the vector position of Q relative to O expressed in coordinates fixed in frame A. So now we know that the rate of change in frame A of the position of Q relative to O, well, that's equal to 0 because L is constant. The angular velocity of A in G crossed with the position of Q relative to O is equal to theta 1 dot E3 crossed with L times E1, which gives that the angular velocity of A in G crossed with the position of Q relative to O is equal to L theta 1 dot E2. So that tells me that the velocity of point Q in G is equal to L theta 1 dot times E2. Now that takes care of the velocity of Q. Now we need the velocity of P relative to Q. Well, the velocity of P relative to Q in G is equal to d dt in G of the position of P relative to Q. But now let's look at the position of P relative to Q. It's expressed in coordinates fixed in the second arm. So the transport theorem here is going to be applied from frame B to frame G. Now we need to compute the angular velocity of B and G, and before we continue onwards. The angular velocity of B and G is equal to the angular velocity of A and G plus the angular velocity of B and A. That's equal to theta 1 dot E3 plus theta 2 dot times U3. But U3 and E3 are the same thing in this case. And since we want everything expressed in coordinates fixed in B when we're all done, this gives theta 1 dot plus theta 2 dot times U3. Now, we can go through the calculus and just do the rates of change. So the position of P relative to Q, its rate of change in B, is just equal to R dot times U1. And the angular velocity of B in G crossed with the position of P relative to Q is equal to theta 1 dot plus theta 2 dot times U3 crossed with R times U1, which gives that the angular velocity of B in G crossed with the position of P relative to Q is equal to R times theta 1 dot plus theta 2 dot times U2. So when we're done with that, that gives that the velocity of point P relative to Q in G is equal to R dot U1 plus R times theta 1 dot plus theta 2 dot times U2. So when we put these two together, what we wind up with is that the velocity of point P in frame G is equal to L theta 1 dot E2 plus R dot U1 plus R times theta 1 dot plus theta 2 dot times U2. Now this may seem a little odd at first because we have things in different coordinate systems, but again, notice that each piece was easiest to differentiate using different transports. The first transport, which gave me the velocity of point Q in frame G, was to transport from A to G because it was most easy to express the position of Q relative to O in coordinates fixed in frame A. Whereas it was most easy to express the position of P relative to Q in coordinates fixed in frame B. So the second part we transported from B to G, not from A to G. Now, it's tempting at this point to want to put everything in one coordinate system, but that's not the way to do this problem. The way to do this problem is to leave each piece alone and differentiate it again separately. We differentiated them separately when we were dealing with position to get velocity, so we should do the same thing starting with velocity to get position. So remember that this is equal to the velocity of point Q in frame G plus the velocity of P relative to Q in frame G. So we're just going to go do the process again. We're going to say the acceleration of point Q in G is equal to d dt in G of the velocity of Q in G. But the velocity of Q in G, I have it written here, but if we go back one step, the velocity of Q in G is expressed in coordinates fixed in A. So this is going to be d dt in A of the velocity of Q in G plus the angular velocity of A in G crossed with the velocity of Q in G. Now, the rate of change in frame A of the velocity of Q in G is equal to, well, it's right here. It's L theta 1 double dot E2 because L is constant and E2 is fixed in frame A. The angular velocity of A in G crossed with the velocity of Q in G is equal to theta 1 dot E3 crossed with L theta 1 dot E2, which is equal to the angular velocity of A in G crossed with the velocity of Q in G is equal to, well, we've got E3 crossed with E2, which is minus E1, which gives us minus L theta 1 dot squared E1. So now I have the acceleration of point Q in G is equal to minus L theta 1 dot squared E1 plus L theta 1 double dot E2. Now that part, the transport was done from A to G. Now we're going to do the second part, which is that the acceleration of P relative to Q in G is equal to d dt in G of the velocity of P relative to Q in G, which is equal to, well, once again, look at the second part of this vector. The velocity of P relative to Q in G is expressed in coordinates fixed in the second arm, fixed in frame B. So this is going to be a transport from frame B to frame G. So this is the rate of change in frame B of the velocity of P relative to Q in G plus the angular velocity of B in G crossed with the velocity of P relative to Q in frame G. Now d dt in B of the velocity of P relative to Q in G is equal to, well, if I look at that vector, I've got R double dot times U1, and then I've got plus R dot times theta 1 dot plus theta 2 dot plus R times theta 1 double dot plus theta 2 double dot times U2. And then the next part of this, which is the angular velocity of frame A and G, angular velocity of B and G, crossed with the velocity of P relative to Q in G, is equal to theta 1 dot plus theta 2 dot U3 crossed with r dot u1 plus r times theta 1 dot plus theta 2 dot times u2, which is equal to, and now we go through the process again of the cross products. We wind up with r dot times theta 1 dot plus theta 2 dot times u2 minus r times theta 1 dot plus theta 2 dot squared times u1, which gives that the acceleration of p relative to q in frame G is equal to r double dot minus r times theta 1 dot plus theta 2 dot squared times u1, and then we have to add up all the u2 terms. So we've got 2 r dot times theta 1 dot plus theta 2 dot plus r times theta 1 double dot plus theta 2 double dot times u2. So now we have both pieces. We have the acceleration of q, which we obtained earlier, and we have the acceleration of p relative to q. So the acceleration of point P in frame G, which is then equal to the acceleration of q in G plus the acceleration of p relative to q in G, is equal to, so let's line this up. It's minus L theta 1 dot squared E1 plus L theta 1 double dot E2, and then we have plus R double dot minus R times theta 1 dot plus theta 2 dot squared times U1 plus 2R dot theta 1 dot plus theta 2 dot plus R times theta 1 double dot plus theta 2 double dot times U2. And you can see that each piece of these, each piece of the vector is differentiated separately, and the final result is expressed in two different coordinate systems. So what is it that we now learn from this? So what we learn here is we learn the following. If we go back to the beginning, we have the following terms. So let's write them down, and let's get a little bit more explicit. The position of Q relative to O is equal to L times E1. This defines the location of Q relative to reference frame A. Reference frame G in this case. The velocity of point Q in G is equal to L theta dot times E2. Theta 1 dot times E2. This defines the velocity of the point in frame B that translates relative to frame A, or frame G in this case, right? So basically this is the translating point, right? So Q is the translating point. So first I started by defining its position, then I got the velocity of it. The acceleration of point Q in G, which is equal to minus L theta 1 dot squared E1 plus L theta 1 double dot E2. This defines the acceleration of the point in frame B that translates relative to frame A. Frame A, keep saying frame A. Frame G, because we're interested in that. Now, the rest of it has to do with the motion of P relative to Q. So again, I start with the position of P relative to Q. That's equal to R times U1. This defines the location of the point of interest relative to the point in B that translates relative to G. So, in other words, I want the position of P relative to Q. I'm interested in the location of P relative to the point in B that translates relative to G, and that point is point Q. So then the velocity of P relative to Q in G, which is equal to R dot U1 plus R times theta 1 dot plus theta 2 dot times U2. This defines the velocity of P relative to Q. Remember again, where Q is the point that's translating relative to the ground, as viewed by an observer in G. And then the last part is the acceleration of P relative to Q in G is equal to R double dot minus R times theta 1 dot plus theta 2 dot squared, this times U1 plus 2R dot theta 1 dot plus theta 2 dot plus R times theta 1 double dot plus theta 2 double dot times U2, and this defines the acceleration of P relative to Q as viewed by an observer in G. So all of that breaks down the motion so that you can actually see, what's going on with point Q relative to the ground and then point P relative to Q. Again, when you take the derivatives, the velocity and acceleration is viewed by an observer fixed to the ground. Now let's do one more example. Let's see how this works and let's do a problem here that has a three-dimensional kind of perspective to it. It's a little bit more challenging problem, but it's a good problem to do to be able to see what's going on. So imagine that I have a disk. Now this disk is rotating on a shaft, if you want to call it that. But the shaft itself is rotating relative to the ground. So this whole assembly is kind of like is rotating like this, and the disk, if you want to think of the rotation of the disk is defined by this angle, which I'm going to call theta. Well, actually, let's call the angle phi. And no, it's okay. We can call it theta. And the assembly, there's a point P on the edge of the disk, and this assembly rotates, but the horizontal shaft, which it doesn't look horizontal in the picture, but it is, and I'll show you what that means in just a second, rotates about the vertical. So you can think of this this thing rotating about the vertical like that. And I'll move the word example away from this so that we can have more space to be able to see what's going on. But this whole thing is rotating relative to the ground, and it's rotating about this vertical direction, omega. I'm going to call this point O. I'm going to call this point Q, and then that point, of course, remains P. This point is P. Now, this is not anywhere near as simple a problem to solve as the first one. So, because you've got rotations, you've got three-dimensional information, and you got to take it into account. So, the first thing to keep in mind is the disk is rotating relative to the arm, and the arm is rotating relative to the ground. So, if I were to look down on this picture, meaning down on the direction omega, what I would see is I would see something that looks like this. I would see an arm, and I wouldn't see much of anything else, but what I would see is I would see this disk. This disk is actually, if you want to actually make this a little bit more visible, imagine that this thing's at an angle, and I'm looking down. So now what's happening is the angular velocity omega is actually out of the page, and the disk is actually here. That's the disk. And this point right here is point Q. And somewhere on this thing, if I'm looking down on this thing, P is sitting right there. P is that point where this angle, if you want to call it the angle between Q and P, if you are the vertical projection of Q, and P is what I've drawn in the picture. Now, what we're going to do is we're going to describe this in terms of we need three coordinate systems because there are two rotations. So we have two rotations. So we need three frames and three coordinate systems. So this time I'm going to actually start by going backwards. I'm going to say D is the disk. And actually, again, I'm going to give myself some more room. D is equal to the disk. The origin of the coordinate system is going to be at point Q. Now let's go back. Now, given that I've fixed point P to the disk, I'm going to put a direction. I'm going to call this direction U sub r. It's going to be along QP. Now look at the axis of rotation. You see the axis of rotation? If I call this point back here O, the axis of rotation is actually OQ. So I'm going to call UZ, I'm going to call that along OQ, and then U theta is going to be UZ crossed with UR. And then I'm going to go back. Now we're going to go to the arm. The arm has its coordinates, and I'm going to actually use the coordinates in such a way that they're consistent. OQ is what I called UZ in this direction. So I'm actually going to call EZ, I'm going to call that direction along OQ. And I forgot an origin, so I've got to put an origin. The origin in this case is going to be at point O. I'm going to say UZ is along OQ to be consistent with the previously defined coordinate system. And now omega is going to be one of my other directions. The question is, do I call it UX? Do I call it UY? Given that I've of the sense of the rotation of omega, I'm going to call it UY, because then UX will be the cross product of those two. So I'm going to say UY is going to be along omega, and then UX is going to equal UY crossed with UZ, and then the last frame is going to be the ground, which is my base frame, and the origin of the coordinate system here is going to be at O, and then I'm going to say EX, EY, EZ is going to equal UX, UY, UZ when t equals 0. Now, what do these coordinates look like? So let's see if we can draw coordinates in such a way that it makes some sense. So here, if I'm looking flat on the disk, then the direction coming out of the page, that's UZ. The direction that's along this direction from Q to Q to P, that direction is UR. That's the way I defined it. And then if I do that, if I take UZ crossed with UR, that gives me U theta pointed this way. And the angle theta is being measured relative to this vertical direction. So this angle here is theta, and then this angle equivalently is also theta. Notice that this direction is actually along omega, even though I didn't call it along omega, but it's actually along omega. I didn't need to because I used UR along QP and I use UZ along OQ. So in this picture, if you actually freeze the directions, and if I get rid of the omega from here, because I just did that just to show you that that direction is actually omega, I defined along omega to be uy. So this direction is actually uy, and then I called the direction along easy. That's the same as uz. And if you take uy crossed with uz, you actually see that you get a coordinate system. You get the third basis vector in this coordinate system, which gives me ux, which actually points that way. Now I have all the information that I need in order to be able to construct the position of P relative to O. So the position of P relative to O is equal to the position of Q relative to O plus the position of P relative to Q. And make this a little bigger. Now the position of Q relative to O, if I call, I didn't define this, probably should, L, the length of the arm, and I call the radius of the disk R, then the position of Q relative to O is going to equal L times that direction that I defined it. I defined it to be OQ, so this is UZ. And then the position of P relative to Q is equal to R times UR. So now when we're done, we've got the position of P relative to O is equal to LUZ plus R times UR. But we don't want to put these in the same coordinate systems. We're going to leave them exactly the way they are, and we're going to differentiate each piece separately. So the velocity of point Q in frame G is equal to d dt in G of the position of Q relative to O. But the position of Q relative to O is expressed in coordinates fixed in the arm, so this is equal to d dt in A of the position of Q relative to O plus the angular velocity of A in G crossed with the position of Q relative to O, which is equal to, well, d dt in A of the position of Q relative to O, that's equal to 0. And then the angular velocity of A in G is equal to omega, which is equal to omega uy. The way I defined it, that direction is uy. So that tells me that the angular velocity of A in G crossed with the position of Q relative to O is equal to omega uy crossed with LUZ, and uy crossed with uz gives me L omega ux. So that tells me that the velocity of point Q in G is equal to L omega ux. Now let's do the second part. The velocity of P relative to Q in G is equal to d dt in G of the position of P relative to Q. But the position of P relative to Q is expressed in coordinates fixed in the disk, so this is equal to d dt in D of the position of P relative to Q plus the angular velocity of D in G crossed with the position of P relative to Q. Now, the angular velocity of frame D in G is equal to the angular velocity of A in G plus the angular velocity of D in A. We already have the angular velocity of A in G. We need the angular velocity of D in A. the angular velocity of d and a is equal to theta dot times, I called that direction uz. Remember, uz is along OQ. So that gives me that the angular velocity of d and g is equal to omega uy plus theta dot times uz. But uy needs to be expressed in coordinates fixed in the disk, and I can get that from this picture right here, which I'll draw again just for completeness. This direction is uy, this direction is ur, and this direction is u sub theta, which makes its opposite direction negative u sub theta, and this angle here is theta. So from this we have that uy is equal to cosine of theta times ur minus the sine of theta times u theta, which gives the angular velocity of d and g as omega cosine of theta ur minus omega sine theta u theta plus theta dot uz. So now we can compute the angular velocity of d and g crossed with the position of p relative to q. That's equal to omega cosine of theta ur minus omega sine theta u theta plus theta dot uz crossed with r ur, which is equal to ur crossed with ur is 0, u theta crossed with ur is minus uz, and uz crossed with ur is u theta. So I get r omega sine theta uz plus r theta dot u theta, from which we obtain the velocity of p relative to q in g is just the second term, because as we already got through saying, the first term d dt and d of the position of p relative to q, so we never computed it. Let's compute it so that we actually can finish this off. d dt in d of the position of p relative to q is equal to 0, and that's just because r is constant, which gives the velocity of p relative to q in g is equal to r omega, let's put it in the right order, r theta dot u theta plus r omega sine theta uz. The last thing we need to do is we need to compute the acceleration of p relative to q in g. So the acceleration of p relative to q in g is equal to, well, if you go back through all of the all of this, you'll see that there's nothing in here that we haven't actually done yet. We've done almost everything at this point, because we don't really have much left to do as far as the this whole thing is concerned. But you know what? Let's actually do this in two parts here. So I forgot to do the acceleration of q. So the acceleration of q, you could do it this way. The acceleration of p in g is the acceleration of q in g plus the acceleration of p relative to q in g. The acceleration of q in g is equal to d dt in g of the velocity of q in g, but the velocity of q in g is expressed in coordinates fixed in frame A, so that's d dt in A of the velocity of q in g plus the angular velocity of A in g crossed with the velocity of q in g. And just to make life a little bit easier in this problem, let's assume that this omega, the magnitude of omega, is a constant. It's not necessary that we do that, but it'll just make things a little bit easier when we actually go through the rest of the algebra. So as a result, we know that d dt in A of the velocity of q in g, that's equal to 0. And that's because L and omega are both constant. If you go back to the velocity of q in g, you'll see that it involves L and omega. And now we need the angular velocity of A in g crossed with the velocity of q in g. That's equal to omega uy crossed with L omega u z, which gives that the angular velocity of A and G crossed with the velocity of Q and G is equal to minus L omega squared u x. Let's see if we did that right. Let's see. So if you look at, no, sorry, this is wrong. This is L omega u x. So this gives uy crossed with ux gives me minus L omega squared u z. Alright, so that's correct. So that gives me the first term. The second, so now I have the acceleration of point q, which is the first term up there, minus L omega squared u uz. Now I need the acceleration of p relative to q in g. That's equal to d dt in g of the velocity of p relative to q in g, which is equal to d dt. Now, given the fact that the velocity of p relative to q, if you look at it, the velocity of p relative to q in g is expressed in coordinates fixed in the disk. So this is d dt in d of the velocity of p relative to q in g plus the angular velocity of d in g crossed with the velocity of p relative to q in g. Now, d dt in d of the velocity of p relative to q in g, if you go back to this expression, you'll see that r is constant, so we've got r theta double dot times u sub theta, and then because omega is constant, you just get plus r omega theta dot cosine of theta times uz. And now we have to get the angular velocity of the disk in the ground crossed with the velocity of p relative to q in g, and that's equal to, well, we went through and got that angular velocity. It's omega cosine theta ur minus omega sine theta u sub theta plus theta dot uz, and then this is crossed with, now we've got r theta dot u theta plus r omega sine theta u z. And now we can put this over here. So we've got omega dg crossed with the velocity of p relative to q in g, and that's equal to, now if we go back over here, ur crossed with, well, let's write it again actually. Let's put this whole thing up on this, so that omega cosine of theta ur minus omega sine theta u theta plus theta dot uz crossed with, and we've got r theta dot u theta, and then we've got plus r omega sine theta uz. So this equals, ur crossed with u theta is uz, so you get r omega theta dot cosine theta times uz. Ur crossed with uz gives me minus r omega squared cosine of theta sine of theta u theta. U theta crossed with u theta is 0, and u theta crossed with uz is ur. So we've got minus r omega squared sine squared theta times ur. And then uz crossed with u theta gives me minus r theta dot squared ur. So, and uz crossed with uz is 0. So this gives that the acceleration of p relative to q in g is equal to, we've got r theta double dot u theta. So let's grab all the ur terms. You got minus r theta dot squared plus r omega squared sine squared theta times ur plus, now the u theta terms, r theta double dot, and then we've got minus r omega squared cosine of theta sine of theta times u theta, and they got plus r omega theta dot cosine theta, but there's another r omega theta dot cosine theta, so you got 2r omega theta dot cosine theta, and that's it. So there's no parentheses needed here. 2r omega theta dot cosine of theta times uz. And so when we're all done, the acceleration of p in g is equal to the acceleration of q in g plus the acceleration of p relative to q in g. And the acceleration of q in g we computed as minus L omega squared times uz. That's equal to minus L omega squared uz, and then we've got minus r theta dot squared plus r omega squared sine squared theta times ur, and then we've got plus r theta double dot minus r omega squared cosine of theta sine of theta times u theta plus 2r omega theta dot cosine of theta times u z. And once again, you'll see that the expressions for the acceleration of q and the acceleration of p relative to q are in two different coordinate systems, because the translating point, the point that's in the rotating and translating frame, that translating point in that frame is its motion is expressed in a separate set of coordinates, or a different set of coordinates from the coordinates used to describe the motion of the point we're interested in relative to that translating point. So that's the key from this discussion, is that you don't want to use the same coordinates to describe the motion of the translating point as you do the motion of the point you're interested in relative to the translating point. That's the overarching theme whenever you deal with rotating and translating reference frames. And as we'll do more problems of this kind as we go on into other parts of the class, but for now we'll stop.